All right, good day everyone. We are here to continue with our Doppler effect. Okay, so this is the third situation that we can apply Doppler's formula, where we have the source of sound, okay, moving towards stationary observer. Okay, so this is the formula. This is the formula, okay, where we have the apparent frequency equating to V on V minus Vs. I said it here is supposed to be S, okay. Then multiplying F naught. Now we realize that the general formula, as we did know from the previous video. Okay, so from the previous video, we know very well that the general formula for Doppler, okay, is F equals we have our V plus or minus V plus or minus V V naught all over V plus or minus Vs. Okay, yes. Then we have our F naught here. So this is our F naught. Now, this is the general formula. And the situation we have at hand, and the situation that we have at hand is that a source is moving towards a stationary observer. So this tells us that there will be an increase in frequency because the source is moving and then the observer is stationary. But this same source is moving in the same direction. Okay, it is moving towards the observer. So it means that as the sound starts moving, okay, so if I have the source of sound being here and then the observer A being here, okay, the moment this source starts moving towards A, the frequency here will start increasing as this source move towards A. Okay, so as this goes towards A hears more of the sound. So it means that we would have an increase in the F. Okay, the frequency, which is the apparent, the one that the observer will listen to, would increase. Now let's get back here. Yeah, okay, so we are there already. So if it will increase, then definitely we should get something like that. So I'm just teaching you the ways you can use to derive your formula for every question. Okay, so this will increase because the source is rather moving towards a stationary what observer. Now, if the observer is stationary, then it means that the velocity here is zero. The velocity of the observer will be zero. So we now have here to be zero. Okay, so we now have this place to be zero. And if here is zero, that means that we can get rid of the plus and minus here. So we'll be left with V as the only numerator. Okay, as the only numerator. Note, F naught doesn't change, but it depends. I told you guys, movement is one of the principal things we consider in Doppler effect, okay, or distance. Let me say it that way, displacement, okay. Now, you now have the velocity of sound in air only, okay, at the numerator. The observer is at a point, a fixed point. So its velocity becomes 0. Now, let's go back to the denominator. Now, we know this should increase. This should increase. So how do we get an increase f with respect to this if you want to deal with a plus or minus? Note that this is a fraction, and if the denominator is bigger, we get a smaller f, and if the denominator is smaller, we get a bigger f. Since f increases, then it means that we should get a smaller denominator. So we consider here, so let me clean what is here. So we consider this part, this plus or minus here. Yes, so we consider here to be minus, so that we would get an increase in f. So the source is moving towards a stationary observer, and this observer will hear an increased frequency of the sound. Note that the previous video we were using a plus here because the frequency would increase. This time around, we are going to hear the same increase in frequency, but the observer is 0. So if the observer was 0 and there will be a plus here, then definitely here is supposed to be 0, minus. So here is supposed to be minus. But in this case, we have the stationary observer and then we have the source moving. So in the case where the source is moving away, that's when we have a decrease in frequency, where here becomes plus. Okay, so let's take note of this. Let's take note of that. So we have this here where we have from 0 to 0. We have an increase in frequency because the source is moving towards a stationary observer. So here becomes minus, so that we will get an increase in the number here. Okay, so this is it. So you can use this formula to solve any question that falls under a source moving towards a stationary observer. So let's go to the second situation, which is the source moving away from an observer. Okay, so the source moving away from an observer. The source moving away from an observer. So let's see. So the observer could be stationary. So in the first place, let's consider the observer being stationary. Okay. So if the observer is stationary, so let's say the source of sound. Okay, let me start from the observer. We have observer A. Okay, we have observer A here at a point, at a phase point. Okay. And then we have a source of sound was here. And then this source is moving away from observer A. This source is moving away from A. Now, we could all figure it out from here that the moment the sound was here, A was getting a higher frequency. But the moment it starts moving, this source starts moving, then we would have a decrease in what? The frequency. Okay, now this time around, A is stationary, so our V naught is still 0. Okay, our V naught is still 0. But this time around, this source is moving away from this. So it means that when it moves away, we have a decreased frequency. So here becomes plus. Here becomes plus because if this denominator is bigger, we have a decreased f. So treat this as a fraction where we have b is equal to c C over D. So when D is bigger, B is smaller. And when C is bigger, B is bigger. Okay, so that is how we do it. Yes, so this is some of the situations that you can apply uh, these laws. And then don't forget to follow the question and get the right solution, okay, or the right formula for the question. Now, let's talk about one last thing, then we end the lessons on the Doppler effect. In some questions, they can ask you to find the wavelength of the produced frequency. So if I say produced frequency, that is the apparent, okay, the heard frequency, the frequency that is heard by the observer. So here you can also say this is observer's frequency. Okay, so we all know that velocity can relate velocity to frequency. Uh, yes, and then lambda. So if you make f the subject, you can replace here with v. So f will be equal to, so most books use c, okay, to represent the velocity. It's the same thing. So we'd have f is equal to v, which divides lambda. Okay, so you can just put this equation here, okay, so that you can look for the the wavelength of the heard frequency, the velocity of the heard frequency, how and it depends on how the question will be put. You can also apply the same thing here. If you have the heard frequency or the apparent frequency, you can also substitute this here to get the other parameters. Okay, so I'll urge all of you to share this channel, subscribe, and let's learn more here. Okay, yes.